In this segment, we're going to investigate polynomial functions of higher degree, and that means polynomial functions of degree higher than 2. As you might imagine, there would be a vast number of functions that fall into this category. And so we're going to make a lot of different kinds of investigations into this area. Now, these kinds of functions are all continuous, that is, they have no breaks in them anywhere, and they're simply curvy, and the higher the degree, generally, the curvier they get. Also, the curvy idea, I want to emphasize here, that curvy means that they do this kind of thing. Now, they might make curves very quickly, but they never have a situation where they go to a particular point. Maybe they curve to a point and then go off in a completely different direction all of a sudden. Absolute value functions do that kind of thing. Well, at any rate, let's begin the investigation with a couple of functions that are degenerate forms of polynomial functions of higher degree. These are not particularly curvy, but there is a characteristic I want you to notice here. If we're thinking about f of x as x cubed, and this is its graph, then g of x is x to the fifth. It turns out that the graph of this function is very similar to the graph of that one. In fact, it'll have a behavior that kind of looks like this. It'll come down and it'll just get closer on the x-axis faster, flatten out, and then do this kind of thing. And if we investigated x to the seventh, it would come down and be even tighter on the x-axis, you see, and tighter over here, and then it would exit much faster, or a little faster, than this other one did. This would be a good time to investigate the idea using your graphing calculator. Well, in a similar way, if we take f of x as x squared, we know all about the parabolic curve, but then a g function, which is x to the fourth, it'll turn out that g function will come down and just snuggle up to the x-axis a little bit quicker than the other one did, and just stay flat a little longer over here, and then go up in a rather big way like this. And x to the sixth and x to the eighth would have similar kinds of behaviors, just coming down really close to the x-axis a little faster than the one before. I've probably overemphasized the idea a little bit too much here in these illustrations, but you get the idea. Now, another thing I'd like you to notice is this, that x squared and x to the fourth, these functions have the same behavior at the extremes of the coordinate plane. That is, they both go up on the either side of the coordinate plane. And on the other hand, x cubed and x to the fifth have sort of opposite behavior at the extremes of the coordinate plane. So we have one side goes up and the other side goes down. That's kind of a general characteristic. In fact, let's explore that a little bit more. If we were thinking about the behavior of graphs at the extremes of the coordinate plane, then this is one thing that's kind of important to realize, that if we were making a table of values, if we were just making a table of values here and putting in points, checking out x's and y's, then with polynomial functions of higher degree, it's pretty easy to see that if we pick values of x that are sufficiently large, either positively or negatively, then the value of this leading term will turn out to be overwhelming in terms of all of the other terms combined. For example, if this is 1,000, then 1,000 cubed is a really, really humongous number. And it is overpowering compared to these other rascals, because this is only 1,000 squared, whereas here we had 1,000 cubed. That's nothing compared to the value of this. Now, because of that idea, it turns out that, you see, in plotting points, we're saying for this value of x, we have a value of y, and so on. But at the extremes of the coordinate plane, all we have to do is look at this term to tell what's going to happen to the graph. For example, here, when x gets really, really big, cubed, humongous, and these don't really make any difference. So when x gets big, f of x, the y value, gets really, really big, so the graph is going to exit the coordinate plane in this direction. And we can make that kind of analysis with polynomial functions. This is called the leading, actually it's a leading coefficient test because it's the coefficient here of the highest agreed term that makes a large difference. Not the numerical part, but the sign here makes a big difference. All right, now notice that we're in standard form here. The term of highest degree is going to be written first in all of the problems that we consider. Now, consider the negative side. If x is a really big negative number, you take a negative number and you cube it, you get a negative result. So when x is big negatively, f of x is big negatively. So that means that the graph goes down at the extreme left of the coordinate plane. So this is just an analysis of the behavior at the extremes of the coordinate plane. Now, consider this one, x to the fourth and so on. Once again, as x gets really big, either positively or negatively, raising that number to the fourth power will cause a value to occur here that overwhelms all of the other terms combined. And therefore, all we have to do to analyze the behavior at the extremes is look at that term. Now, think about it. Really big x value. All right, if x is really big positively, to the fourth power, still positive. So when x gets big positively, f of x gets big positively. So that graph is going to go this way. If x is a big negative number to the fourth power, though, is positive. So when x gets big negatively, f of x is going to get big positively, and so we have this kind of behavior on this side. Now, we don't know much about, at this point, about the curves in between. We don't know how many there are or how the behavior is. We're just looking at the extreme behavior. Now, think about what happens if I make a little change in this first graph. All right, I just make this minus, the negative of. Well, if x is a big positive number and it's cubed, x cubed is a big positive number. So as x gets big positively, f of x seems to get big positively. But the negative of that big positive number, this value is negative. So as x gets big positively, f of x is getting big negatively, and the graph goes like this. On the other hand, if x is a big negative number, a negative number cubed, negative. But here's the opposite of that negative number. That's positive. So as x goes this way, f of x goes this way. So that's how you analyze these things. Now, one important aspect of these two functions compared to one another is this, that the cube function has opposite behavior. That is, the behavior at one extreme versus the other is going in the opposite direction. Whereas an even exponent as in the leading term, in the highest agreed term, will cause the same behavior on both sides. Now, if this were negative, both of these arrows would be pointing down. You see, like this. Okay, so that's the idea. Now, let's look at some other characteristics here. Suppose I take this one off. And let's suppose I want to examine some aspects of the graph in between here. Well, I would start by making a table of values. That's the fundamental thing that we can always fall back on, is a table of values and the point plotting method. Well, let's see. I've created a table of values associated with this function, and here is that table. And I just started at -3 and I progressed all the way up to 4. Now, let me plot some of these points. Well, let's see. -3, -18, -3 goes down to -18. That's off the graph to the left side. Now, we already know from our leading coefficient test, leading coefficient test tells us about behavior at the extremes. All right, with the leading coefficient test, we know that, now, let me make sure, let me come back over here, and I had added this minus sign. I don't want to mislead anything right here. I want to take that off, because my leading coefficient test tells me that as x gets big positively, f of x gets big positively. As x gets big negatively, a negative value cubed will be negative, and therefore f of x will be negative. So that tells me that the graph goes down as x gets big negatively. And that's what we're verifying here with -3 going to -18. All right, so it begins to get negative really fast here. on that side. All right, negative 2 goes to 0. I've plotted that point. Negative 1 goes to 4. I've plotted that point. 0 goes to 0. I've plotted that point. 1 to negative 6. Here's that point. 2 to negative 8. Here's that point. 3 to 0. Here's that point. And then 4 goes to 24, and that's off the graph to the high side. And that's what we expect from the leading coefficient test. So here's how we construct the graph. Now, we're just sort of connecting dots from one side of the graph to the other. And if we're thinking about from this side of the graph over here, let's see, this 4 went to 24. So from somewhere off the graph up here, we come down and we go through this x-intercept. And we come down, and this looks like a relatively low point right here. So we come down and we grab that, and then we come back this way. But wait a second. Is that a minimum point or a relative minimum point? Well, you know what? We don't really know. We're not sure about that. That is an absolute relative minimum point, because the graph could go down a little bit over here and then come back up and hit that point, or it could go through that point like this, and then it could go down and then come back up like that. You see, we just don't know if this is a relative minimum or not. Some of the techniques in calculus are designed to identify the exact relative minimum and maximum points. But just because it's the lowest point that we're graphing here doesn't necessarily mean it is a relative minimum. All right, we'll treat it that way just for the time being, but I want you to know that it's not necessarily the case. All right, the graph comes up, goes through the origin, comes up here, goes through this point, not necessarily a relative maximum for the same reason as the other one was not a relative minimum, and goes through this x-intercept, and bam, out the coordinate plane like this. So there we have the graph. Now, we can discover aspects of the graph, namely the intercepts, by factorization. That is, if we had taken our original function, like here, and factored it, I see a common factor of x, and I see a trinomial that I factored x minus 3 times x plus 2, then I can identify the x-intercepts very easily. The x-intercepts are the zeros for these factors, and those are solutions of the f of x equals 0 equation. If we replace f of x with 0, 0 equals this. Solving that equation means we want the values of x that cause each factor to become 0. Those are solutions of that equation. They are x equals 0, x equals 3, x equals negative 2. Solutions to the equation, they are zeros of the function. They are x-intercepts when thought of like this. So those are kind of interchangeable parts. Now, the zeros help us jumpstart our thinking in this whole process of analyzing the graph. So we're using the leading coefficient test and the zeros of our function to start the process. Before I leave this problem, though, there's one very important thing I want to point out to you, and it's this, that this idea of going from a factored form into the zeros or the solutions is reversible. That is, if we know that 3 is a 0, then x minus 3 is a factor of our function. If negative 2 is a 0, then x plus 2 is a factor. And after all, I mean, we can just take this and manipulate a little bit. This is x plus 2 equals 0. You see, it's that idea that x plus 2 is a 0. X plus 2 is a factor. Same notion here. X minus 3 equals 0. And so the x minus 3 is a factor here. X equals 0, and then x itself is a factor up here. All right, that's an idea that we're going to come back to a little bit later. All right, let's go through this process again, thinking about using the leading coefficient test and the zeros, or the x-intercepts, to guide us in the process. We start with our function, and then we go through a factorization. All right, so the common factor is negative 2x squared, leaving x squared minus 4. Oh, happy day, it's the difference of squares, so we factor into the sum and difference of terms. Now the zeros, the values of x that will cause each factor to become 0 are, let's see, x equals 0, x equals -2, x equals 2. We start our table of values by saying, well, if these are zeros, they are x-intercepts. They are places where the y value is 0, so 0, 0 is on the graph. -2, 0 is on the graph. 2, 0 is on the graph. Let's stop right here. Don't look at this just yet. We would probably graph this, okay? Plotting those points, we would get these 3 points. Doesn't tell us a great deal. Let's use our leading coefficient test to make some decisions here about the nature of the graph. Back up here. Leading coefficient test. Look at the -2. Now, we have an even exponent on x. That tells us that the behavior is going to be the same left and right. All right, that's about all it tells us. Now, if this value is positive, we know that both sides go up. If it's negative, and since it's negative, both sides go down. So the graph exits south on both sides. That is, from here, it's probably going in a rather big way down that way, and in a rather big way down that way. Now, we'd like to know something about the behavior of the graph in this region. So, let's see. We've got kind of a hole right here at -1 and 1. So we would go back and use that information from the graph and come back over here to the algebraic form and evaluate the function for x being plus or minus 1. When x is plus or minus 1, we find y to be 6. So we go back over here and we plot. 1 goes to 1, 2, 3, 4, 5, 6. -1 goes to 6 as well. All right. Now I'm trying to emphasize the notion here that in this process of investigating the behavior of the graph, that you make a few algebraic calculations. You go over to the graph and you examine the graph a little bit. You build it just a little bit. And then that information that you have on the graph will lead you to something else, that you go back to the algebraic form. You go to the geometric form of the graph. Then you go back to the algebraic form, back and forth, until you have completed your investigation. So that's the emphasis here. All right, so the notion is that the graph comes up to this point, and then it's got to come back to that point. But it's not going to go through this point. You see, if it went through the point, then it would have to come back up. You see, if it came down and went through that point down here, how is it going to get back there? Well, the only way is to go back through the x-axis, and that would create another x-intercept. So it doesn't go back through. It doesn't go through that point. That is, it comes up here, and this is not necessarily, again, a relative maximum, but we'll treat it that way. Comes down here, and boom, it bounces off of that point, and then up here and back down this way. So that's the behavior of the graph. Now, why did this bounce occur? That's one other aspect of this particular problem that I want to point out. It bounced off of that point because of the factor x squared. That is, within a certain neighborhood here, within a certain interval of x values, the behavior of the graph is similar to the behavior of x squared. You see, it's parabolic. It's kind of parabolic in that kind of neighborhood. So when we have multiple factors or several factors of the same kind, it creates this kind of bounce behavior sometimes. Let's take a look at another function that has multiple factors of the same kind. Now, when you first look at the function, you don't realize that. We would just see this as a fifth-degree polynomial function. We might think to ourselves, well, by the leading coefficient test, we see that we have a fifth-degree leading term, and therefore we know that the behavior on the right-hand, left-hand extremes of the coordinate plane is going to be different graphically. We see that this coefficient is positive, so the graph is going to rise to the right and fall to the left. So we just know that much at this point. Now, we might also realize that there would be at most 5 x-intercepts. You see, it turns out that the degree of the polynomial corresponds with the number of possible intercepts. Now, we may have less than 5, but we can have at most 5. And that's been true all along with polynomial functions of any degree. A first-degree polynomial function, a linear function, has a graph that's a line. The line can cross the x-axis in one place at most. A second-degree polynomial function, the quadratic function, the graph is a parabola. Now, that parabola may cross at no points at all. I mean, think about it. If the vertex is above the x-axis and it opens upward, then it doesn't cross the x-axis at all. Now, if the vertex is on the x-axis, then it has one x-intercept, just at one point as the x-intercept. And if the vertex is below the x-axis and it opens upward, then it'll have two crossings. But at most, two crossings because it's second degree. So fifth degree, at most 5 crossings. Now, we would go through a process of factorization and we would find the factored form to be this. Now, when we see multiple factors of the same kind, it represents a limitation of the number of possible intercepts, and we'll see why that's the case in just a second. But we would begin our investigative process of the behavior of the graph by identifying the zeros involved in the function, and that means we're finding the values of x that will cause each factor to be 0. This factor is 0 when x itself is 0. This factor is 0 when x is 2. So 0 and 2 are the zeros of the function, and therefore the points 0, 0, and 2, 0 are on the graph. We would go over and plot those points. Oh, let's take a look at them. We don't know much about the behavior of the graph at this point. We might want to know something about the behavior between the 2 points. So we would find f of 1. So we go back over here and enter 1 in this column, evaluate for y, we find y to be -1. So we know that the graph intersects here. It goes through the x-axis here, or maybe it just touches here, and then it comes down, reaches this point, and comes up and touches here, or maybe goes through. We don't know quite at this point. Well, we need some information about the graph outside of these points. So we might find f of 3 and f of -1. So we slide back over here. F of 3 turns out to be 9, f of -1 turns out to be -27. Now, as expected, 3 goes to 9, that is 3 goes up. The graph exits upper right and lower left. That's what we're finding out by identifying these points. So f of 3 goes up here at 9. It's about off the graph, I think. F of -1 goes to -27. It's way off the graph. Now, here's how we evaluate the nature and the behavior of the graph in this neighborhood. We're looking at an x squared here, and the x squared behavior, we know, is the parabolic behavior. And that behavior will occur at this point. You see, at the 0 corresponding with x squared. So we'll have this kind of parabolic idea within this little bitty neighborhood, and then the graph goes down and goes through this point. Now, this is the 0 corresponding with x minus 2 cubed. Now, this cubing idea, though, tells us that the behavior in a particular little neighborhood right around this point is the same as y equals x cubed. You remember the graph kind of flattens out at that point and then goes up again? Well, it'll have that behavior right through this region, kind of like this. So that's what's going to happen. Here's another problem involving a rather interesting situation. Now, this function is unfactorable. We would look at the function, we'd say, okay, it's a third degree polynomial function, and therefore there'll be at most 3 x-intercepts. That's about all we know right now. We would try to factor, we can't factor conveniently, so we make a table of values, and we pop in a bunch of points. Well, -1 went to -4, and 0 to -2, and 1 to -2, and 2 to 2, 3 to 16. All right, so I've plotted those points that fit into my coordinate plane here. Now, what I do know is that the left and right-hand behavior are different from one another, and since the leading coefficient is positive, I know that this graph exits upper right and lower left. All right, that's what I know. Then, now notice I've completed part of the graph here. -1 goes to -4, that's here. 0 at -2, 1 to -2 as well, and then 2 goes to 2, and 3 goes to 16 and off the graph. Now, we have a little curve in the graph right in this neighborhood, and we can tell exactly the nature of that curve by looking at the graphing calculator, and we may do that in a few minutes. But what we're really interested in is the position of the x-intercept. Now, we know that f of 1 is -2, and f of 2 is 2. So, since the polynomial functions are continuous, we know that we have a crossing within this interval. Now, we know it sort of intuitively, but we also know it by the intermediate value theorem. And I want to elaborate on this intermediate value theorem just a little bit because it appears in several mathematical forms. In addition to the course that we're studying here, it also appears in geometry and in calculus. Now, I heard a rather interesting explanation of the intermediate value theorem from a wonderful mathematician named Howard Eaves. He's one of the leading math historians in this country. And he was asked to explain intermediate value theorem, and he says, well, it's kind of like this. If you find corn growing in a field in March, and it's 1 foot high, and then in October it's 8 feet high, then at some point in time between March and October, the corn is exactly 5 feet high. At some point in time, it is exactly 3 feet high, and so forth. And there is a point in time corresponding with every height between 1 and 8. See, and it's the idea here that within this interval, there is a point somewhere such that f of that x value will give every value between -2 and 2. So there is some x in here such that f of that x gives every value between -2 and 2. That's what the intermediate value theorem is all about. So we know we have a crossing. Now, what are some techniques? Let's talk about techniques for identifying the crossing. We don't know quite where it is. We know we might guesstimate, I guess, that it's around 1.5, 1.6, 1.7, something like that. And we might use this, a technique of taking half of the interval in which we know there is a crossing. That is, we could say that, well, it's between 1 and 2. Let's evaluate f of 1.5. So then you'd come out to the side and you would evaluate that. Now, I've done it over here. I know that f of 1 is -2 and f of 2 is 2. Now, because these are opposite signs, I know there's a crossing between 1 and 2. So I split the interval and I find f of 1.5. All right, f of 1.5 turns out to be this. Notice it's negative. Now, that means that because at 1.5 we're negative and at 2 we're positive, there is a crossing in that interval. So we're kind of narrowing the interval. Now we take the midpoint of this little interval between 1.5 and 2. Well, that's at 1.75. And we find f of 1.75 to be 0.297. Aha, it's positive. So there must be a crossing then between these two. That is, at 1.5, f of 1.5 is negative, below the x-axis. F of 1.75 is positive, above the x-axis. So the crossing is between these two. So we could take half of those. So that's one technique, this kind of midpoint idea to try to identify the intercept. Another technique that works pretty well is to just subdivide the original interval into tenths, you see, and evaluate at 1.1 and 1.2 and 1.3 and 1.4 and so on. And then when you get consecutive tenths that turn out to have an opposite sign, that is, f of maybe 1.6 is negative and f of 1.7 is positive, then you know you have a crossing within that interval. And you could divide that interval then into tenths. They take tenths of the tenths, you see. So that's another technique. And there are other techniques in calculus as well that you'll learn about in time. Well, the graphing calculator is particularly adept at finding an x-intercept very quickly like this by using some of the zoom features. Let's have a look. The function has already been entered. I would like to call your attention to the way that x cubed is entered and the way x squared is being entered. X cubed must be entered by pressing the exponent button and then follow that by 3. And then this is minus and then x, and the squared business can be entered by pressing x squared on the calculator or by pressing an exponent button and then a 2. But this is probably, it's a one button push here to enter it this way. All right, using our standard settings, and I'm just pressing a 6 here on the zoom menu. This is what the graph looks like, and we saw it a moment ago. Let's press trace and see if we can identify a pretty good approximation of that x-intercept. Let's see, I'm in the neighborhood of the x-intercept right now. looks like it's about 1.7 and so on, and notice the y component is positive. So y needs to be 0 for us to have an exact x-intercept, and we can get a lot closer to that by pressing zoom, and then we'd like to zoom in. So I'll cursor to number 2 and press enter, and now what we have is a centering icon, and here's the centering icon, by the way. There it is, and I'm moving it down to the position of the approximate position of the x-intercept. And now the centering icon is just right at that intercept, and I'll press enter again, and I'll just keep getting a magnification of that point. Now that centering icon is not necessarily a point on the graph. To make it a point on the graph, I would have to press trace, and now we have a point on the graph. And if I cursor to the left and then to the right, I'm seeing that I'm straddling the x-axis. I get a y negative here, and arrowing over to the right one, I get a y value that's positive, negative, positive, negative, positive. So the actual x-intercept, or 0, is a number x that's between this 1.688 and so on and 1.70 and so on. And I can get more and more accuracy by continuing to use the zoom and trace buttons on the calculator.